Hello, this is the INQA seminar series. Today with us we have McElvain from Berkeley, and he's going to tell us about fermionic Schrodinger equations solved by an adiabatic quantum computer. Please begin.
Okay, well, thank you for inviting me to talk about my most recent work here. All right, I'm just going to jump in. Let's see what. Hold on. Okay, so the objective here is, we have some interesting Hamiltonian, and we want to, find the ground state. We're going to just, make it discrete over a finite volume periodic lattice in first quantization, so it's not second quantization. Some example target problems that are interesting are, say, the fractional quantum Hall problem, or perhaps 3D nuclei. This is the direction I'm heading. My background is in nuclear effective theory, doing shell model calculations, things like that. So that's how, what my focus was getting into this. Okay, so the key challenge turned out to be the Laplacian, and that was true in the distinguishable particle case, which I'll review briefly in a moment. And so I've got the Laplacian approximated here on the lattice, where I'm sampling the wave function to the left and right of a given site, and minus 2 times the central value divided by the spacing of the lattice, and that gives me the second derivative. And these references here are equivalent to motions of the particle, and those interact with the exchange symmetry. All right, so I'm going to just give a little quick background on the distinguishable particle version of this, which is published, and I had some collaborators with that, Cheng and Rapaj and Wu here in, let's see, that was 2022. And I'm going to build on this. I'm just going to describe it briefly. One of the key notions was to encode position with gray code. And the advantage of a gray code is a code, it's an encoding, say, of an integer, where as you go from, say, integer 3 to integer 4, the code will only change in a single bit. And so that has the advantage that the sigma x operator will basically generate those neighbor contributions. And the trick with, we went one step further with this thing called a Hamming distance 2 gray code, and it's this green path on this diagram. This is a 4-variable encoding of 8 positions, and those are the positions along the green path. And you can see that as you go from this position, which would be encoded 1 1 0 0, here's the 1 1, there's the 0 0, and you flip one bit, 0 1 0 0, and you flip a bit, and you flip a bit. So every step along here, there's a specific bit that's flipping in the encoding. And so sigma x is going to generate symmetric contributions between each pair of states along that path. And these red ovals are penalties, so that we're not going to, and they're large penalties, so we're not going to occupy these states. We're going to suppress it. And so you'll notice that the sum of sigma x you see down here would generate a contribution into this site that has the penalty, but since it's a suppressed state, it filters that away. It's kind of like a trash can. These penalties are kind of like the trash can for the unwanted contributions of sigma x, leaving only the ones along the path, the contributions along the path. And so, we demonstrated this work very well with the, simulation. So the first thing we did is adiabatic quantum computing. We start in a completely transverse state and turn on that penalty, those red ovals. And then we follow up by turning on the the potential. So this was a harmonic oscillator example. And so you can see what happened to the wave function. We start out kind of with the uniform occupation of all the states. We turn on the red oval penalties, and then we've concentrated onto that one path, and it's still uniform, which is what you'd expect. And then we turn on the potential, and and the familiar harmonic oscillator ground state appears. And so this was done, we did a full simulation of this, and it worked beautifully, actually. So now we move on to identical fermions. This is kind of the new work. So kind of basic stuff, our fermionic state, say for 4 particles, is a Slater determinant, or say we take 4 position states, A, B, C, D. Those are just positions on our lattice. And so then I'll write the state down as just the list of states. Those are the states that are involved. And if I think about it from a distinguishable particle point of view, then it would, then the ordering would matter, right? But because they're all identical fermions, the ordering doesn't matter. So what we do, or what I do, is I choose the one that satisfies A less than B less than C less than D. So I pick one of the 4 factorial product states and say that's going to represent my fermionic state. Okay. So you can imagine I have particle 0 and particle 1, and they have positions. And so this, in a 2-particle case, if they have the same position, then that has to be prohibited, because that, Pauli exclusion principle. And then if particle 0's position is less than particle 1's position, then I'm going to exclude those. That's an ordering prohibition or penalty I'm going to apply. And then these are the states that we're going to let the system occupy. And if you go to higher dimension, it'll just be this corner of that, space. All right. And then you can also add in another penalty to make it non-periodic, if you like. And that can actually simplify the resulting circuit a good amount. So if we're going to go from distinguishable particles to fermions, let's take an example here. I've got 2 particles, 0 and 1, and I've got their gray codes here labeled. And so the little double-headed arrows are those sigma x contributions for the between adjacent positions that are generated by the sum of sigma x. And you can see they wrap around. And so now I'm going to be imposing this penalty over here. And then most of these connections, the symmetric connections, are actually valid. And the ones turns out I'm missing are the ones that have to do with particles going off the end of the periodic order. And that means that, let's take this one, for example. If that's 1, 3, and if I increment 3 to be 0, that would take me here. But I have to go to I have to jump instead to the partner state, where I flip the ordering. So I repair the ordering. And so next thing I'm going to do is talk about some tools I'm going to use to do the repair of the ordering in several different cases. So the first is something I call an entanglement gadget. And our first exposure to entanglements usually a 2-qubit wave function. And qubits A and B are always in opposite states. And these 2 qubits carry the same information. And in an entanglement gadget, we add a contribution to the Hamiltonian that is turned on by a projection operator when they're in conflict. So in this case, if the 2 qubits agreed, either both up or both down, we'd add this penalty. And then, as we're turning all of these penalties, the ground state will not contain, the basis states that lead to that conflict. Assuming we turn on the penalty slow enough, yeah. Okay. And then, actions on spin A can be replaced by actions on spin B. Now, one optimization is that in more complicated examples that are going to come, these projection operators, you might be able to write simpler projection operators that overlap. And so there'll be cases where more than one of these conflict projection operators is on at the same time. And that's perfectly fine that you've got some cases where your penalty is 2 times Q or 3 times Q. And that turns out to simplify the generation of the conflict contribution. So an important one is the ordering case. I want to prohibit all of these states that are in the lower left of this diagram. And so valid orderings have the ordering of the first particle or position of the first particle, the index of it has to be less than the index of the second one, and so on. And so the unordered or conflict case, I can write as the sum of those things. So basically, I need a projector for this and a projector for this, and I can add them up, and that will prohibit being down here. So since I'm using gray code for the positions so that I can use the sum of sigma x to generate the Laplacian, I want to have also maintain the position in binary, because it turns out I can implement the less than operator more easily in that encoding. So I'm going to have the same information represented in binary and in gray code, and then use whichever one is the easiest for the task. So here's the way I think about doing these things. So you can write an expression to generate gray code from your binary bits. This is very standard. And so this is the XOR operator, Boolean XOR operator. And so what I'm going to do is go through bit by bit between my binary and my gray code, and I'm going to write down a projector for the case where the XOR of these 3 things is true. And if you just write down all 8 cases, you can find the 4 projection operators that you need for that. In this case, they don't overlap, but so in any case, this will, if you sum these up across all the bits and you add that into your Hamiltonian, it will make sure that you have both gray code and binary representations of position. Okay, and these are all intended to act on, if you think, the way I think about it is acting on basis states. So then I also need the less than projector. So I'm going to, again, write out a Boolean expression for it and then translate it into a projection operator or a sum of projection operators, to be applied in the quantum computer. So the XOR, it's the same. I can create ancillary bits that represent that XOR in the same way I had to do it for the binary gray entanglement. And then this is a standard, what's called ripple carry implementation of the less than operator. And so you can write it out in terms of those bits as if they were Booleans. And you'll notice that on the right, I have a one size smaller less than operator. And so kind of inductively, if I can do the base case and I can show that I can build the next higher width less than from that, I can just inductively show I can build the whole thing. So here I end up with an ancillary qubit representing the smaller less than operator, and then I've got to write a projection operator on 4 qubits to specify the, to find the case where A is less than B. So it's pretty straightforward. Also need rotation operators. And so we start with a swap, which has this kind of straightforward implementation in terms of poly operators. And so for 2 qubits, a rotate left or a rotate right is just the swap operator. It's the same thing. On 1 qubit, it's just the identity, so don't worry about that. And it turns out you can compose these things. The way I think about it is you can partition your sets of bits. You can apply a rotation operator to each partition. And then you can, for the rotate right, you take and you apply another rotation operator on the leftmost bits. You can kind of draw this out for yourself and you'll see it works just fine. And there's an entanglement gadget trick to kind of break this into layers with some ancillary qubits so that it doesn't just get, very large. So now that I've got my rotation operator, let's actually apply it. I'm going to start with the simplest case. So I'm going back to my diagram of the 2 particles. I've got some particle that's on the edge of the periodic space, meaning if I get a motion to the right, it will wrap. And I'm wondering, asking if I have this space state, what other states will the Laplacian make a contribution to? This is that sum of sigma x again. So it's going to generate 0, 3 going up. It's going to generate 2, 3. Wait, 2, 0, 3. Where did I get to 0, 3? 0, 3. Good. And it can get to 1, 2 here, and it can get to 1, 0 by wrapping. Right. So now we're making a contribution to one of the penalized states, which isn't so useful. So this red state's not ordered. So how do we recover? Well, you can insert 1 minus the swap operator, and now you're going to generate pairs of states. This is where you have the identity, and the second one's where you've done the swap. And so you'll notice that we've added 3 new penalized states to our list, which is immaterial because they're suppressed. But we did recover our 0, 1 state that basically wrap and then go to its partner by exchanging the 2 fermions. And because we exchanged it, that's what this point of this minus sign is right here. Whoops, let me go back. The point of the minus sign is to track the phase associated with the exchange. And then if we're going to do this more generally with more particles, we need to actually apply a rotation to all sets, the whole set of particles. That's why on the previous slide I was talking about rotations over multiple groups of variables. So think of these as acting on all the bits, say all the gray code bits of the position, and rotating them together for a set of particles. All right, so now we need to talk about 2D, because that was all 1D. In 1D, we had the advantage that if you incremented a particle position, it either found an unoccupied position, in which case the ordering was still good, or you incremented it and found an occupied particle, in which case it was suppressed anyway. So the only way to get an unordered state from the application of the Laplacian was by wrapping, in the periodic space. So once we go to 2D, though, we can have a vertical motion. So here I've got a state 5, 7, 8, and I'll write it down with the properly ordered. So there, you know, the first one's less than the next is less than the last. And when I move, when I apply the sigma x that would move the particle in position 5, it would make a contribution into position 9. I generate 9, 7, 8. Well, 9, 7, 8 is not ordered, so I need to apply rotation operators. So rotation to the left here would wrap the 9 into the position where the 8 is, the 8 goes where the 7 is now, and the 7 would go to the 9. And now you have a properly ordered state. So I need to, at each position in the set of particles, not in the set of, not in the exponential number of positions or anything like that, but just in the number of particles, I have to build rotation operators at various lengths, and I have to include the phase associated with that rotation operator. Okay. We can also subset those rotations because, you know, this is quite a few rotations going up to A, but I'll point out that if we've increased n being the number of lattice points in any direction, then the number, you know, with a fixed A, then eventually the number, the chance that you're going to actually get many of your A particles in that one little space is quite low. And I think it's valid to increase n, you know, thereby dramatically increasing capital N, and then limit the range of the location of the rotations to just a few particles. And that's one of the things I want to try simulating if I can figure out how to simulate that many qubits. So to summarize, the Hamiltonian I'm constructing here is the potential plus a set of penalties, one for the what we call the Hamming distance 2 gray code. Those are those red ovals that kept the path isolated. There's the unordered penalty, which restricts us to the set of properly ordered states. And we could add in this, optionally, this non-periodic penalty, which actually I'm kind of assuming is in here for this equation right now. And then we have to go through all of our entanglement gadgets and add in their penalty contributions. And then finally, doing the real work in that context, we have our sum of sigma x for, let's say, an H2, you know, for the Hamming distance 2 gray code, Hamiltonian acting on those rotations. And I should point out that this sigma x, when it acts on these rotations, these are rotations of all the position information of particles. So it's actually just, you know, rotating the full position. So each sigma x that comes in, it acts only on a slice of that rotation operator. So it's not as big as you'd think. But in any case, the whole thing is, you know, polynomial in A and little n. So there we go. Yeah. So in conclusion, I have a cost for building a circuit that's polynomial in A to the D. So actually it should be D minus 1 and n. And, you know, the number of basis states we're solving over is exponential in little n. So, you know, we have polynomial cost and exponential amount of computation going on. And, you know, this idea of operator filtering, where I take an operator and I put it in a restricted space so that I get the behavior I want, you know, that green path when I was talking about the Hamming distance 2 gray code. And then also important here were the entanglement gadgets, which I'm using to simplify the number of operations. For instance, maintaining the position both in binary and gray encodings. And then one thing I should have mentioned earlier, I guess, is working in a finite volume protects the gap between the ground state and the first excited state. This is something we found in the earlier paper. And this protects the rate at which we can introduce the penalties and introduce the potential. So the whole thing actually works quite well. All right. And thank you. I guess there are no
Yeah, thank you
questions.
for the nice talk. I'll ask some questions now. Uh, I guess the most immediate question would be that you seem to have used a bunch of penalties in your
Yes.
construction, and do you have some sort of a summary of what kind of resources are required from a quantum annealer to implement those penalties? Like how many qubits how
Ah,
many qubit terms are there, for example? How large are this interact? Or I mean, how many qubits are these interactions acting on simultaneously?
yes. So for example, let me just back up to here. So when you like this Hamming distance 2 gray code, you have these penalties, right? And so it's actually a quadratic number of polyweight 3 operators for that. That would be, this is one of the bigger cost uh, penalties in the system. The others are much more local, in the sense that if let me give you an example. So these they're products of projection operators, but it's a fixed, I don't know, I guess it's a fixed cost here. So it's not scaling with the size of the numbers you're doing less than on, right? Each of these contributions. So it's linear in the size of the numbers that you're doing, applying that you're enforcing binary gray code with. Does that make sense?
Sure.
It's
So, and
bit,
the
it's
follow-up,
bit by bit instead of,
yeah.
so you don't have to worry about the size of the numbers.
Well, so the follow-up question here is, you mentioned some sort of swap operators. So does it mean that you need your XX and YY terms in your Hamiltonian?
Yes, you do need, uh, you will need, especially for the rotation operators. Yeah, this construction does need, a complete set of, poly operator products. So, and I know that's not so available right now. So I'm just looking to the future, hoping that will be available.
Yeah,
Now,
that's
there
very
is,
interesting gadget theoretically as well. I mean, I didn't know you could do this with swap operators. Um, all right, so you can finish what you were saying.
yeah, no, I think that was kind of all I had to say on that.
Good, good. So then, let's wrap it up for today and um, see everyone next week.
All right.